In this video, we're going to take a look at gas laws, Gay-Lussac's law and the combined gas law. Gay-Lussac's law relates pressure with temperature. For an enclosed gas that has a fixed amount and also a fixed volume, then we know the pressure and the temperature are directly related. As one goes up, the other one also goes up. When on the Kelvin scale, that relationship is pressure divided by temperature of the initial sets of conditions equals pressure over temperature for the final set of conditions, or a second set of conditions. So as one goes up, the other one goes up, or if one goes down, the other one also goes down. Again, when on the Kelvin scale. Any unit of pressure is okay because the pressure units are able to be converted. They are direct relationships, unlike, again, temperature where you have to add and they're not a direct proportion. So let's take a look at a Gay-Lussac's law problem. So aerosol cans, they carry a warning saying do not throw them into an incinerator or store above a certain temperature. The problem is what we're going to discover here, why you shouldn't do that. So gas, when it's in an aerosol can, is at a pressure of 103 kPa and it's at 25 degrees Celsius. If I were to take that can, throw it into a fire, what will the pressure then be when the temperature reaches 928 degrees Celsius? So let's analyze and figure out what we know and what we're trying to solve for. So we know that the initial pressure is 103 kPa and the initial temperature is 25 degrees Celsius. And again, I can't use Celsius, so let's convert that right into Kelvin, and it's 298 Kelvin. And then I'm trying to solve for the second pressure, where's the pressure inside the can, once it heats up to 928 degrees Celsius. And again, we'll change that right away into Kelvin, and we'll add 273, and that's 1,201 Kelvin. So again, the law that relates that is Gay-Lussac's law. P1 over T1 equals P2 over T2. And we're going to solve for P2, so I'm going to multiply both sides by T2, so that way I can isolate P2. So T2 reduces out, it gets me P2 all by itself, and I see P2 equals P1 times T2 over T1. Now I can substitute in for my variables the values that I have. So 103 kPa times 1,201 Kelvin divided by 298 Kelvin. The Kelvins reduce out, and I get an answer of 415 kPa. So roughly 4 times the pressure that we would have at regular atmospheric pressure when it heats up to 928 degrees Celsius. And that's why this is so dangerous, because that amount of pressure is going to cause that can not only to just explode, but send shrapnel flying everywhere and take off kind of like a projectile. And then the second law we'll look at is the combined gas law. This is going to take all three of the gas laws and put them together. Boyle's law, Charles' law, and Gay-Lussac's law. And it's going to relate pressure, temperature, and volume for any enclosed fixed amount of gas. So anytime pressure, volume, and temperature are changing, then we're going to use the combined gas law. And as you kind of see, if you cover up each of the different variables, if I were to cover up temperature, I'd have Boyle's law. If I cover up volume, then I'm going to have Gay-Lussac's law. And if I covered up the pressure, then I would have Charles' law. And all three, again, here together in the combined gas law. So here's a real-life situation where you'd see this, a combined gas law problem. We have a diver. He fills up his lungs with a breath of air to 6 liters on the surface where it's 30 degrees Celsius and the temperature is 100 kPa. But then when he dives down to a depth of 5 meters, now the pressure increases to 150 kPa, and then the air that's in his lung is going to warm up to his body temperature, which is 37 degrees Celsius. What is going to be the volume of his lungs at this point, 5 meters below the surface? So let's go ahead and analyze and list out what we know and what we don't know. Let's kind of read through the problem. I know that the initial volume is 6 liters when he's up at the surface, and the temperature is 30 degrees Celsius. We'll convert that right into Kelvin, so 303 Kelvin, and that initial pressure is 100 kPa. Then when he dives down, the pressure increases to 150 kPa, and the temperature increases to 37 degrees Celsius. What is that new volume going to be? So again, we use the combined gas law. It's going to relate all three of these variables of two sets of conditions to each other. So P1 V1 over T1 equals P2 V2 over T2. But we're solving for V2, so we have to isolate V2. So we'll divide by P2 and multiply by T2 to both sides. And then I find the equation V2 equals P1 V1 T2 divided by T1 times P2. And then I can plug in my variables, 100 kPa times 6 liters times 310 Kelvin divided by 303 Kelvin times 150 kPa. And then when I solve this out, Kelvin reduces out, kPa reduces out, leaving me with liters, and I find the new volume to be 400.09 liters.